Last Monday, just summary of what we gone through last Monday. So first thing is we learned about types of retaining systems, right? Agree? So we know about we also talked about how do we design them. Yeah. So this includes retaining walls, includes all types. We talked about sheet piles, cutting piles, secant piles, diaphragm walls, and other king post and panel type of systems. Those are the systems that we learned how to hold the ground. Whether you are digging 3 meters deep, whether you are digging 30 meters deep, what type of systems we should use. We talked about the design of them, a little bit about what we should consider in terms of the design. Yep. Agreed? And then we also talked about the types of risk assessments, damage categories. Yep. So, risk assessment, which includes damage category. Depending upon the type of the structure. So today I'm going to touch in continuation of those. Today we're going to talk about now, we know a bit of design, we know what wall we should be putting in this, given a sort of a site constraint. I'm going to just go through methods of construction. So how do we actually build the basement, given if that is the ground level, or where you've got already a basement of one level, how do we deepen it? How do we make it 5 levels deep or 6 levels deep, whatever the client wanted. So I'm going to briefly touch on what we call top-down. Top-down means we build top-down, as it says. And we also do bottom-up. So this is actually digging everything out and then building from bottom-up. Or it's a mixture of those things, it could be a hybrid scenario. Then I just touch on props. So how do we hold the ground as we dig? We talked about props, we put props as we go down. Even if you are actually doing top down, what sort of props we should put, where should we put it, when should we put it. And then installation, and also it's important how you can remove them. I think I talked to you about last time I touched. These props are, depending upon the size of the basement, they are very big. We're talking about 10, 15, 30, 40, 50 tons. You've got to remove them. So you've got to think as an engineer, how do we actually remove those props while the construction is going on? Yeah. And then observational approach is about a procedure where we put the monitors. Obviously, there's a lot of learning through this observational approach. It's like what you do in your laboratory. You take a sample, you test it, or you take concrete, you test it, you see the results, and then you improve on those. So the observational approach is an approach where you continuously monitor the systems, not just the ground, but all the surrounding properties. And I talked to you about the stakeholders. How do we gain the confidence of stakeholders? How do we ensure people are comfortable with the sequence that you are proposing is safe for their structures, whatever is structure surrounding your building or the client's building. I just touch on those 3 aspects today. So if you remember this particular one, where one can see this is going to be clearly, okay? Is it bottom up or top down? Yes, absolutely bottom up. So you can see here, we're talking about 2 levels of basement surrounded by all buildings, massive site. We're talking about from there to there, 130 meters, 70 meters building. So what is the beauty of this, what we call also a blue sky option? Is it? So what is the advantage of that blue sky? What do you see there? Yes, I agree. But what from construction point of view, a planned point of view, personal point of view, health and safety point of view, what do you see there?
No uncertainty.
Yeah, ground uncertainty, yes.
No uncertainty.
Yeah.
Once you've excavated, there's no uncertainty. Everything's
Yes, I agree. So you know what you're digging, you know the material, what, yeah? You know, when you're digging, you know what is coming out. You know, obviously, that uncertainty, as you keep digging, you know what the material you're digging is. That's fine. What else do you see there? It's the amount of space, isn't it? It's a huge space where plant can move easily, very safely. The space is not constrained. Anything to do with the construction. Remember, construction industry is where most of these serious accidents happen. And in fact, we are killing people. We should not be. We should be safe home, Yeah, always whoever, working on industry, we want to make sure everybody is safe on site. They come to work safely, they go home safely. That's our principle. So the safety, you can see the improvement in terms of the plant movement, personal movement, material movement, logistics. The crane, tower crane is operating with almost 30-40 meter jib here. It's lifting concrete, it's lifting steel, it's lifting all sorts of cladding materials. So the beauty of this blue sky option is the amount of space that we create for all the logistical operations, which can be done very safely. It's a blue sky option. You can see clearly what you're digging. As you say, you can see what material you're going through. You can also see how you're operating each and every corner of the site so that you don't sanitize the whole site. So the things are left, open space, and you can see how you monitor each and every area. So that's the blue sky option. That's it. So one of the things with the blue sky option is obviously you got to think, how long does it take to dig all of that volume? Yeah? So here, the situation is that the time permits you to dig. If you imagine, as I said, these are roughly about 100 meters, that's 50 meters, so 5,000 times, let us say 10, including your bulking, we are talking about 50,000 meter cube of muck coming out from that site. And in London, there are restrictions on how many lorries you can take on those highways in the peak hour moments. So the construction hours between 8 to 6, whatever 8 hours that are stipulated, the council or the local government, local authorities impose planning conditions that you cannot take more than 100 trucks out. Every truck carries only no more than 10 meter cube of concrete or 10 meter cube of muck, so you can only take 1,000 meter cube. So time is essence, number of wagons that are going out of the site, how you actually pull all that muck, and where is it going, whether that material is contaminated, or all those aspects you have to think in terms of doing a blue sky option. Yeah. So this particular one, to excavate all this, it took about 8 months to take the material, pull it out. So in terms of bottom up, the blue sky option, so your ground level is somewhere there. As you can see, this is the dashed line is an existing structure. So that's where existing walls, existing foundations, which is a typical scenario when you are digging next door to any of the buildings. So these are the existing foundations, you can see here, the existing walls, and all that needs to be retained, and we are digging very close to it. So the dashed line is where the structure is, and we are actually now deepening the structure to this level. So what we are trying to do here is, we do the sequence of sheets from this level, because that's where we are operating from. We push the sheets, and then we drop the ground, we excavate to this level, we put what is called veiler to hold it, and then put a prop and a thrust block. And then you start digging to the formation level. This is called the formation level. So, obviously when you put a prop here, you need a thrust block. Obviously the force is coming from there to push the wall, the force is going through there. So you need a chunk of concrete here, right? So, but your ground is there. So how do you put that chunk of concrete here when your ground is here? Yeah? So you have to create a local pocket from here, from the ground level, at that level. So basically you create a trench here, because your ground level is here, you create a trench, you create that lump of concrete, and then as you dig down, you anchor it. So you need a thrust block to hold it. That's because we have got raking prop. This is called raking prop, because the prop is obviously raking. You may have a fly-through prop, then you don't need this one. So you go from one end to the other end. So if the box is done, like last time we saw, if you got a box of a reasonable dimension, so you put a fly-through prop from one end to the other end. Because this is a shallow excavation, if you start doing this one, this is going to be very expensive. So we want to hold the wall as much as roughly reasonable depth and is equal to reasonable width. In terms of that dimension and that dimensions are reasonable, we just hold it by raking prop. So the advantage here is you are only creating thrust blocks locally as you go. So if you got a wall you are holding by a raking prop, you create a hole here from that ground level, create a thrust block, and do another one at 7 or 8 meters, the next. So the spacing of these props, you put it in such a way the machine can go in between them. You can have number of them. Obviously the size of this block depends on the force that you are generating here, because this structure is all pushing it, yeah? Right? So that force is more if you keep them very large spacing. If you keep them close spacing, as we discussed last time, the plant cannot get in. So you've got to make sure a balance of what is the spacing of the props versus spacing of the... So if you can see here, that's what we have done, raking prop. Yeah? So the beauty is that you can see the size of these machines can get in. If you want to do any piling or any other work that you have between them is about 8 meters. It's more than dimension that way. So that's the same dimension. You can keep them very close spacing, it'll be very tight. You can see if you keep them very close, then the size of this prop will be reduced or increased. What happens if I keep them very close spacing? What happens to the force there? Yes, small. So if the force is small, my thrust block is small, my prop is small, easy to handle. But my plant cannot get in, so there's no point. So you've got to achieve a balance between the prop spacing and what the plant movements are, and also think about this thrust block. Remember this thrust block, we created it when the ground level is here. We created a hole, we put a thrust block. Yeah? So this is a sort of, most of the times, depending upon the scale and the time program, we go for what is called a blue sky or a bottom of construction, and that is how. So that's how a raking prop is used. So when you start building the wall, so you can see here we have removed it, because now we build the slab, we build the wall here, so we can knock out. So again you got to think about at what stage I should remove it, because that prop, as I said, is about 7 or 8 tons. You need to detach this and you need to lift it out to build all the things that are going in the basement. So that's another sequence. So again you got to think of the removal of the sequence. So this is one thing that we saw before. It's a massive basement surrounded by very important buildings in the center of London, in Fenchurch Avenue. That dimension is about 60 meters, roughly about 65 meters dimension. So the way that we looked at that is in terms of construction. There is an existing basement here, which is there. And there are existing walls, existing buildings you saw there. So the way to do is to obviously go a minimum distance, do the secant piles here, and then we put what is called, in the secant piles, we put what is called plunge column. So it's basically when the concrete is done, you drop a steel post inside it, and that will hold the existing wall. And then start digging, as you can see here. Next sequence is to hold that to a thrust block that is grounded, and then when you dig, now that is cantilevering, you construct the capping beam as we discussed. Now we are dropping the ground from there, straight there after you install the prop. Yeah? See what I'm saying? This prop, is it a fly-through or a raking prop? It's a fly-through, yeah? This is a fly-through. So this is actually from going from one end of the building to the other end of the building. So the beauty of this is again, the amount of volume that you are getting here, the amount of space that you are getting, the amount of logistics that you can do within that site is really amazing, and that is where health and safety of whole personnel working on site is improved dramatically. So we have to think in terms of building, in terms, if you are going from bottom up, what aspects we should be thinking about. And again, you got to think what volume is coming out. And remember, this prop, as I was saying, is very big prop. You got to think how you install it. So you drop it, so your ground is here, we install it while the ground is here. That's another thing, so we don't have to suspend it. And when we install the prop onto the capping beam, we talked about capping beam last time, remember? So when we install the capping beam here, we want to cast that together. So that basically it gets locked in, so there is no slack in the prop. Sometimes we also put a jack here to make sure it picks up the forces. So if there is any slack, that prop is not going to, wall will move, then prop will start taking the load. We don't want any undue movement here, because that existing party wall, he will be watching, or she will be watching what is happening to that party wall. Those people will be looking at how much the wall is moving before you install. So you install, you lock it here, then you start digging sequentially to the formation level, which is that. So every meter you dig and then take it out, and then that's where you go. And then you start building. Once you build a raft or a piled raft, whatever you have here, then you start building bottom up. So that's the sort of sequence that we use for very large basements where again time is permitted. So you can see clearly the other aspect that you should look at is what are the obstructions in the ground. So if you got a lot of obstructions in that particular job, we have 3 meters of grillage pads. So this is spread entire footprint of the building. We got existing foundations. So you have to dig them out because you already put the prop there. So you dig them. So you are working with all knowns because you are digging sequentially. You are opening up the existing foundations because before you start, most of the time you will find the existing foundations. There is no map. They can't tell you because London has got so much of history of building on site again and again and again. A lot of historical stuff that has happened on the site. We do not know. We find some foundations there, some foundations there. And sometimes you get a good archive information, sometimes the client may not have that archive information. So another beauty of this method is as we are digging down, we are exposing these things and we are nicely dealing with as and when we see it. So that is the beauty of it. And also, when you go to the formation, you can see, as you were saying, the site, what material we are bearing on, what is the material we are dealing with, how do we deal with, all the aspects are taken care of. In this particular scenario, you can see we've got terrace gravels and we've got London clay, a lot of obstructions on site, and that bottom-up construction gives a fantastic, safe approach to construct that basement. That is the reason we chose. This is another big site. We're talking about something like 70 meters by 70 meters. So again, it gives you a sequence that we normally go through. The red ones are the existing foundations. So that's where we are. You can see the existing foundations, existing neighboring properties. So we bring the piles, we do the piling from that level. Next stage is we actually start dropping the ground after we construct the capping gate. Sometimes you may have to, as I talked about, the plunge column. We insert the steel plunge column, and that will hold the wall by means of rakers or stubs here to hold it. Then we sequentially drop the ground, and then we put a fly-through prop. As you can see, this is the plan view of the props. Spaced nicely for the plant to move, and then also gives you logistical operations for all other things that are going on the site. And so once you install the prop, dig further, and then next stage it shows you how we go sequentially. So we put the prop already, so now we can start dig around. And then second level of prop if it is required. Sometimes you feel, you remember I told you know the deep depth of the foundation and also the structure, adjacent structures. You have to decide how many props you have to put here. Yeah, it is limited by, obviously if you actually leave this, the bending moment on this is going to be huge. Yeah, because the forces are coming this way. So the bending moment is going to, imagine this is like a simply supported beam. So the bending moment diagram will be that. So if you put only one prop, because of the load that is coming, so you probably get that sort of thing. So the bending moment is very high. Whereas if you put multi-prop system, you've got a continuous system. So you've got a prop there, you've got a prop there, you've got a prop there. So you can see the bending moment diagram comes like that. So it's reduced. Yeah, it's like a continuous beam for all the loading that is applied. So you have to decide whether we should put 2 levels of props or 3 levels of props, and then proceed sequentially to the next level, to the formation level. And then you got, as I was saying, now you've gone down to the bottom, so you've got to think how you are building it up. So we build a slab at this level, then we are moving up, so we build a floor there, because that is one basement. So when you build that basement, you can see that prop is already gone. Yeah? So, and then we build the next one, you can see when you put that one, that prop is already removed. So you sequentially build every floor bottom up. So this is another sequence. So what happens is, in that scenario, you've got a multi-strutted excavation. Not single level, but it's a multi-strutted. So that's all right in terms of a bottom-up blue sky option. Sometimes, what happens is, we have got, it takes a long time to dig it out, but I want to progress on the top. in construction wise. So how do we do it that in that case? Because the volume that we are excavating is so huge. This site here, we're talking about 500 meters by 500 meters, spaced with grid of columns. Generally, a grid of columns is about 7 or 8 meters. So this is a place where we are extracting gravel here, because what we found there was we got 8 meters of gravel below the ground level. So we are taking a gravel and it's going into concrete. Yeah? So we are creating space. Now what happens here is that if you start excavating all this, you can imagine 500 by 500 by is about 10 meters. Is a massive amount of stuff coming, very close to the airport, restricted by the number of lorries, which is very, very slow dig. So what we normally propose in that sort of scenarios is we start first piling, that's your ground level. So we'll do the piling at regular grids, because that to tie up with the column spacings of the grid. And then we put what is called plunge columns, as I was saying. So you got a bore, so your piling is done from here, concreting is done to that point, and then you drop a steel beam or a steel column UCs, and that is your plunge column. Once you got that, then you still have not dug here. Yeah? The piling rig is still moving on the ground, doing simply the piling and plunge column. And what we are doing then is, on the ground, using that as a bottom support, we pour concrete straight on this. You see the advantage? Normally, if you are pouring a concrete slab, you need to put a shutter, right? So you got to put the shutter. Here, we are using ground as a support for the shutter. So we cast concrete slab here. So, means you can start working on the slab before you start digging. So we have to do a lot of landscaping here. This is gravel extraction. So basically we are doing the tunneling. We are actually mining. We are mining all the gravel here, taking it out, also creating a landscape and a natural park and communities and all the stuff that can go on top of the deck. So while we are doing all that stuff here, I am doing all the landscaping, all the creation of park, recreation facilities, coffee shops, whatever, visitors, everything is happening on the deck. So we are building while we are digging below that slab. Make sense? Yeah?
How many gaps did you need to get on?
Right, yeah, I'll come to that, yes, yeah, exactly. That's a very good question. So obviously, very important. What do we need to get the muck out? Yeah? So normally, for any big sort of space like that, for any, if you actually, you can probably compartmentalize it. If a team is working here, you want at least a 10 meter by 10 meter, what we call a molding hole. Yeah, mold hole. So obviously the stuff that is going to be jumped, or whatever you're excavating, it comes into the center of the site and then it taken out by a long reach excavator. So you need a minimum dimension of at least 8 meter by 8 meter with all the clearances, so the mucking machine can stand on top of it and take it out. That's one way of doing it. Second way of doing it, if you got space, you put a conveyor. Yeah? So the conveyor comes out, so the guys who are digging here, they just dump it to the conveyor comes up. Because this is a very large site, there is scope for the conveyor to be used again and again. So we put a big opening here, 8 meter by 8 meter. Through that the conveyor belt goes there, and then you start digging underneath the deck. Yeah? So the molding hole depends on what is the plant operations, how much stuff that you are digging, how much you are dumping in the center of the site so that you can take it out, how many excavators are operating, how many equipment is actually taking, how much you are taking out per meter. There are long excavators.
From the start, you put the pile down, but you put the pile cage in. The couplers that go down to the second level below,
Yeah.
how do you make sure that they're at the right level, so that when you do break them out, how do you find the coupler to the next slab?
Yeah. What we use something on template. So when you do the piling, you got a temporary casing. In the temporary casing, when you drop the plunge column has got a connection to the slabs. Yeah? So the plunge column will have shear studs. So this is the plunge column that is going into the pile. That is fabricated to the accurate levels. Yeah? Because this is steel, we can control it. Now when you drop it, this will have a template all around it. because it's the casing, so people can control the tilt of this, and it's got a plate, 2 levels of plates here. That plate covers the perimeter of the casing. So when you drop it, it cannot go anywhere. So it's actually got 2 levels of template where people can control the tilt of it, and there is a bit of a tolerance here and there, 10-15 millimeters. So by the time you get down to expose the plunge column, so you've got a casing there, so the plunge column gets in there, there's a template there, there's a template there. So when you actually cut the piles, you can see the shear studs on the plunge column ties up with the floor levels within the gaugeable tolerances. That's the floor level you are going to tie up. Yeah? You see what I'm saying? So yes, it is very difficult to control the plunge columns, and if they go out of alignment, you quite rightly that we must get the floor connections within the tolerances of no more than 10 millimeters. Because it is a steel column, because we've got template that goes into the casing, that is how they control the tilt of it, and the longer it becomes, it's difficult to control it. So that's another thing, we can't have a plunge column that is very long. So once you are in here, so there are 2 operations. Either you could do a molding hole, which is a reasonable size, or you can have, depending upon the site, you put a conveyor and all the muck comes out. So the beauty of that is now we are extracting gravel here, we are mining it from underneath, we are operating this one. So the program wise, you've already built, by the time you go down to the next level, so we build the floor, first floor, B1, and then we go to the next level. So we go to the next level, we dig it to the next level. So whatever the 2 levels, 3 levels we are digging, we just have to keep digging while we are building this. So the beauty of this is the advantage in the program and the cost. And then you are actually letting all the operations that are happening on the deck, whatever we have to do early, much earlier than what, because the volumes that are coming out are huge. It takes very slow dig. This dig is about 4 years, sometimes it's 5 years, because the site is so massive. To create, we are extracting 3 million meter cube of gravel from the mining. So this site, so it's a very slow process, but this is an existing park. They're converting that park into a sort of recreational space, as well as creating all the facilities for the community while we are digging the gravel. So that's a sort of a top-down construction. So again, what happens in top-down construction is, as you can see, you fix the deck here. Yeah, we've already built the deck. So, are the movements likely to be low or high if there is an adjacent structure here? When you start digging, what happens? Do we get less movements or more movements compared to a bottom up?
More.
More in this case?
When you start digging away, you're slowly through.
I agree, but I am comparing this case to a situation where there is a blue sky. Suppose I am doing blue sky. I am doing this blue sky. Yes. The reason is we already locked in at the ground, so the wall cannot go anywhere. So the perimeter wall that you have done, so this is the perimeter wall I talked about, secant, whatever sheet pile, whatever we are doing, whatever you choose depending upon the ground. In this case, because we are locking regularly, we lock that on the deck, we excavate it, we lock it again. So we got the second floor. So it's nicely held up at every level. So it's actually spanning between the floors. Yeah? Rather than what you saw earlier, for a blue sky is spanning very 15 meter high, sometimes 10 meter high, sometimes more than that. So it's like that. So whereas in this case, every floor you are building, as you go down, the floor is only spanning between the floors. The wall is spanning between the floors. Yeah. So the bending moments are controlled. You got less control in terms of, you got a better control in terms of the movements to the adjacent structures and so on. So that's the top-down sort of a scenario. So in terms of the loads, now we need to know, to size the prop, to size the wall, we need to know what the loads are on the props and also on the wall. What are the loads that are applied? Last time we talked about, we have to think about surcharge loading, we have to think about any existing foundations. We talked about water pressures, burst water main. We also talked about earth pressures. Yeah, depending upon what happens on this side of the site when you are digging on this side. So there are various ways of computing these prop loads and forces into the structure. I think one of the simplest thing is what is called DPL method. It is no brainer. It's very simple, easy, quick to do. It's called distributed prop loads. So what this tells you is, I mean, you can use the finite element analysis, or you can do the finite difference analysis, or you can use beam and elastic foundation approach. All sorts of approaches you can do. But this particular one, I like it because it's very simple to estimate for a preliminary design. So what this tells you is, supposing you got multi-level props, so you are digging on this side, the pressure is applied on this side. So if you got a multi-level props, 1, 2, 3 levels, it's a very deep basement. So this tells you what is the approximate load based on the catchment of area of those props. Yeah, just like any other building column load. How do you work out a column load? Take the area, catchment area of that prop. Catchment area of that prop is this. Catchment area of that prop is this much. Yeah. So it's basically a uniformly distributed load method. So you can calculate if you got actually a scenario where a simple way. If I'm putting, let us say, 2-level prop, and that's my formation. If that is 5 meters, and that is 5 meters, let us say I have idealized my project distribution to 100 kilopascal, let us say. Whatever you have done, the total summation is that. So that could be at pressure, it's an idealization, surcharge, water pressure, everything. I know we talked about water pressure like that, surcharge, Coulomb's friction and all that, but I will come to that later on. Why I have used a rectangular rather than a triangular one, yeah? Normally, Rankine scheme is all about triangular project distribution. Same thing with the hydrostatic. But I will tell you about why I have used a rectangular one. So if you got, let us say 100, just for argument's sake, if you take a simplistic approach of 100 kilopascals, so what is the load on this prop? So the distributed load on this prop, if I am putting a prop there, so it will be, if you take 100 times, the prop area is that much here, times 5. Yeah? Makes sense? Whereas this one will have, the catchment area of that is half of this spacing. So this will be 100 times 2.5 is the load. Because the spacing of the props is 5 meters, half the load will go in there, half the load will go in there. It's like a simple beam, yeah? Simple concept. So once you know this is 250, so you can see the top ones will have less load, bottom ones will attract more load. Because the catchment area of that prop is very high. So you get some load half this way, so that's the catchment area. So once you start introducing second level of props and third level props, the prop load keeps going up. So that's another thing that you have to think. So the prop size, if the load goes up, again the prop size is very big. Again you have to think how to take it out. Yeah? So this method tells you, so if my props are spaced at 10 meters, yeah? So if the, let us say prop spacing is 10 meters. So my total force on each prop will be times 10, right? Here it will be 500 times 10. So we're talking about 5,000 kilometers, 500 tons of load on the prop. That raking props, that fly-through props, whatever we talked about, is roughly about 500 tons. That's a sort of order of magnitude. Whereas if you put only one at the top, the forces will be half. Yeah? So you can, if you are digging, let us say 20 meters, yeah, you have to think of multi-level props and then work out the load on those. Now, coming back to the idealized project distribution. So why do we use a sort of an idealized distribution? Why not a Rankine style? Yeah. So I will come back to on that. So this is where you can see the prop is kept only one level props at the capping beam level, and then we are digging right down to the bottom. This one prop. Spacing of these props will be about that spacing. You can see it's equally divided. See that is 50 meters, roughly about 10 or 15 meters. So there's a prop there, there's a prop there, there's another prop there, there's another prop in those corners. Yeah? So you know the spacing of the props, you know the load, and you manage the forces on those props only. because most of the London, the materials that we come across in London are very over consolidated. That means there have been a lot of drifting deposits in London. Some areas it could be 10 to 12 meters. So the London clay has already been subjected to very high pressures in the past. So you will see in Rankin's earth pressure, where you draw your active earth pressure and passive earth pressures using your free values and what, there is a plateau that is achieved in London clay. So you will see, depending upon the type of the soils that you get different distributions. A lot of measurements have been taken place in London clay and also in gravels and within across the site. And they classify that into 4 categories. One is normally and slightly over-consolidated, B is heavily over-consolidated, and the coarse grained is C, mixed soils is D. So there are 4 classifications that have been done. So if somebody comes to you and says, right, okay, this is my site, then you need to be looking at, is this over-consolidated? Has it got coarse grained material? Has it got a London clay that is very stiff? You've got to ask those questions and classify to those A, B, C, D. Once you classify them, then this is the approximate pressure distribution. So A, F is a very stiff wall, and B is a soft wall. So you can see here the pressure distribution. If that is the height of the dig, 20 meters, 30 meters, 10 meters, that's the depth of the basement. Because you got very close to the ground, you get a bit of less pressure distribution. As you go deep, you get what is called as plateau, a steady state condition of 0.3 gamma H. If it is a soft with a stable base with AF, again type A, then you can see different distribution. Soft clay with enhanced base stability, you get different distribution. So that's the pressure distribution at the back of the wall, which is idealized, which is the load that is pushed into the walls and the props. So you can do if you do a Rankins sort of scenario, you will say, okay, right, if it is H, I will put 0.3 gamma H, yeah, and you are overestimating your loads. But because the clay is heavily consolidated, over consolidated, to take the movement, you need to apply, you need to calculate, you need to actually overcome what is the normal consolidation pressure. You are not reaching